Lagrange Point L2, 1.5 million kilometers from Earth, the orbit of the James Webb Space Telescope. At this point, 1.5 million kilometers from our planet, the most expensive scientific instrument humanity has ever built is floating in space. The James Webb Space Telescope. It took 30 years to develop. The total cost reached $10 billion. The heart of this telescope is its primary mirror, 6.5 meters in diameter. 18 hexagonal segments made of beryllium are arranged in a honeycomb pattern, and the surface of each segment is coated in gold. Gold was chosen for one reason: to maximize infrared reflectivity. The oldest light in the universe has been traveling for billions of years, and over that time its wavelength has stretched into the infrared range. To see the beginning of the universe, one must see in infrared. The previous generation telescope, Hubble, orbits just 560 kilometers above Earth. Webb was placed at the Lagrange Point L2, 1.5 million kilometers away. This is a gravitational equilibrium point, where the Sun, Earth, and telescope remain permanently aligned. Beneath the mirror, a 5-layer sun shield, the size of a tennis court, is deployed. Its thermal blocking performance is equivalent to SPF 1 million. The mirror operates at -233 degrees Celsius. Only at this extreme cold can infrared observation function. Launched in December 2021, after a 30-day voyage, it entered L2 orbit. 6 months of mirror alignment and instrument cooling followed, and in July 2022, the first observation images were released. From that moment forward, the history of the universe as humanity understood it began to shake. Lagrange Point L2, 1.5 million kilometers from Earth, the orbit of the James Webb Space Telescope. In May 2025, a research team noticed something unusual in an existing observation image. Among thousands of galaxies packed into a deep field image, one small point was shining far brighter than anything around it. The team aimed Webb's near-infrared spectrograph directly at the object. A spectrograph splits light into its component wavelengths, allowing scientists to determine how far away an object is and what elements it contains. The result was staggering. The object's redshift value was 14.44. Redshift is the phenomenon in which light from a distant object is stretched to longer, redder wavelengths as the universe expands. The higher the value, the farther away and the older the light. A redshift of 1444 means this light was emitted just 280 million years after the Big Bang. If the universe is 13.8 billion years old, this galaxy existed when only 2% of cosmic history had passed. The galaxy was named MOMZ14. Its diameter is approximately 240 light-years. The Milky Way spans roughly 100,000 light-years, making MOMZ14 about 400 times smaller. Yet this tiny galaxy was forming stars at an explosive rate. It surpassed the previous record holder, JWST Z140, at redshift 1418, becoming the most distant galaxy ever observed by humanity. According to existing theory, a galaxy this bright should not exist at this point in time. An object the standard model of cosmology never predicted had been observed in reality. Lagrange Point L2, 1.5 million kilometers from Earth, the orbit of the James Webb Space Telescope, 280 million years after the Big Bang. What was the universe like at that time? According to established cosmology, the universe was still in what is known as the cosmic dark ages. Hydrogen and helium gas produced immediately after the Big Bang filled the universe like fog, and not enough stars had formed yet for luminous galaxies to take shape. The standard model describes galaxy formation as a sequence. First, hydrogen gas begins to gather under gravity. When it compresses enough, nuclear fusion ignites and a star is born. Stars cluster together to form star clusters, and star clusters merge into primitive galaxies. This entire process requires a minimum of several hundred million years. Yet MOMZ14 was already shining as a galaxy, just 280 million years after the Big Bang. If gathering gas into stars and stars into galaxies takes hundreds of millions of years, then a galaxy existing at 280 million years means there simply was not enough time. What makes it worse is the brightness. MOMZ14 was abnormally bright for a galaxy at this stage. That brightness means stars were forming inside it, in massive quantities at extraordinary speed. This directly contradicts what existing models predicted. Two possibilities have been raised. One, the rate of star formation in the early universe was far faster than anyone had estimated. 2, the age of the universe itself may be wrong. Either way, the current framework of cosmology requires revision. Lagrange Point L2, 1.5 million kilometers from Earth, the orbit of the James Webb Space Telescope. MOEM's F14 was not an isolated case. Since Webb began observing the early universe, hundreds of small reddish points have been detected repeatedly. Researchers call them little red dots. Initially, they were classified as ordinary distant galaxies, but as spectral analysis progressed, unexpected results emerged. A significant number of these red points were not galaxies at all. Hidden inside them were massive black holes. The problem was their size. At a point only a few 100 million years after the Big Bang, supermassive black holes weighing millions of times the mass of the Sun already existed. The conventional path for black hole formation goes like this. A star is born, lives out its life, explodes, and its remnant collapses into a black hole. That black hole then absorbs surrounding material and gradually grows. Following this path, reaching supermassive scale requires billions of years. Yet these were already that size within just hundreds of millions of years. In January 2026, a new simulation study was published. It proposed that the little red dots are direct collapse black holes. A direct collapse black hole forms when a cloud of hydrogen gas does not pass through the star stage at all, but collapses directly under its own gravity into a black hole. Because the intermediate step is skipped entirely, a massive black hole can form in far less time. If this is confirmed, the existing timeline of the early universe will need to be fundamentally rewritten. Lagrange Point L2, 1.5 million kilometers from Earth, the orbit of the James Webb Space Telescope. The Hubble Space Telescope was launched in 1990 and has led humanity's observation of the cosmos for more than 3 decades. Hubble's primary mirror is 2.4 meters in diameter. Webb's primary mirror is 6.5 meters. In terms of light gathering area, Webb collects roughly 6 times more light than Hubble. But the real difference is not size, it is wavelength. Hubble observes primarily in visible light and ultraviolet. Webb observes in infrared. As the universe expands, light from the oldest objects has shifted from visible wavelengths into the infrared range. Hubble's eyes cannot see this light. Only Webb's eyes can. When Hubble spent hundreds of hours exposing a single patch of sky for its famous deep field image, that region appeared to contain almost nothing. When Webb turned to that same region, thousands of galaxies came pouring out of the darkness. Many of those galaxies were objects at redshifts above 10, entirely beyond the reach of Hubble's instruments. MOEM Z14 sits at redshift 1444. That is a realm Hubble could never access. For 30 years, Hubble showed us the universe. But in truth, it had not even seen half of it. The picture of the early universe that Webb is now revealing is forcing a complete re-examination of the theoretical framework built during the Hubble era. The universe seen in visible light and the universe seen in infrared occupy the same space but present entirely different landscapes. Lagrange Point L2, 1.5 million kilometers from Earth, the orbit of the James Webb Space Telescope. What Webb is changing extends far beyond our understanding of early galaxies. In February 2026, a new study using Webb data was published. The most precise dark matter map ever created by humanity. Dark matter emits no light and absorbs no light. It is completely invisible to electromagnetic observation, but it exerts gravity. Where dark matter exists, light bends. This is known as gravitational lensing. When light from a distant galaxy passes through a region of dark matter, the gravitational pull warps the light's path, causing the galaxy to appear distorted from its original shape. Webb analyzed these distortion patterns and reverse calculated where dark matter is distributed and in what concentrations. What the results revealed is an astonishing structure. The universe is not uniform. Dark matter is spread across the cosmos in thin filaments, resembling a spider's web. And at the points where those filaments intersect, galaxy clusters gather. This is called the cosmic web. The existence of this structure had been theoretically predicted before, but it had never been observed at this level of precision until now. Without Webb's infrared observation capability, this map could not have been made. Invisible matter forms the skeleton of the universe. Every galaxy is arranged along that invisible framework. Webb is not reading the universe we can see. It is reading the blueprint of the universe we cannot. Lagrange Point L2, 1.5 million kilometers from Earth, The orbit of the James Webb Space Telescope. Redshift 14.44. 280 million years after the Big Bang, this is currently the most distant galaxy ever observed by humanity. But it may not be the last. The research team wrote in their paper, Previously Unimaginable Redshifts, approaching the era of the very first stars, no longer seem far away. Webb was designed for a 10-year mission, but because less fuel was consumed during launch than expected, its actual operational lifespan has been extended to over 20 years. There is still time. The Nancy Grace Roman Space Telescope, scheduled to launch in late 2026, has a field of view 100 times wider than Webb's, allowing it to identify far more candidate galaxies. If Webb then turns its precision instruments on those candidates, galaxies beyond Redshift 1444 may be found. 280 million years after the Big Bang, 200 million, 100 million, perhaps even earlier, humanity's gaze is moving ever closer to the starting point of the universe. The number 13.8 billion years is not a confirmed fact. It is an estimate based on observational data available to date. What Webb is showing us is the possibility that this estimate may need to be revised. The first light of the universe. On the day that light is observed directly, we will finally learn the true age of the cosmos, and that day may be closer than anyone imagined.